Welcome back to RN Talks Physics. We are into circular motion and we are going to discuss the equations which relate to the circular motions in a trajectory guided by angular acceleration. The kinematical equations which we had, like S equal to ut plus half at square, and then v equal to u plus at, then v square equal to u square plus 2as, all those kinematical equations in linear translational motion can be converted to the equations in circular motion, kinematical equations for a circular motion. The basic helping ideas would be, which we discussed in the previous discussion, that in any circular motion s is equal to r theta. Oh, by the way, let me introduce. This is our website, entrances.co.in. Log into our website to get all the details that we offer as courses and programs. Well, let's get back. S equal to r theta. Then we have v equal to r omega, and then acceleration at equal to r alpha. Now this is the tangential acceleration, this is the tangential velocity, and s is the motion along the arc of a circle. Once we are through with all this, they are related through the radius. They are related through the radius of the circular trajectory. So that means, if suppose in kinematical motion, if we have an equation S is equal to ut plus half a t square. Let's say it is moving along a circular arc like this. Say for example, along a circular arc such that from the center it is at a distance r, and from point A it moves to point B, and let's say this particular situation is through an angular displacement of theta, and the particle moves with a tangential velocity generating a tangential acceleration at, which are related like this. So here there is of course an omega involved, and there is an angular acceleration involved. And now if we divide this entire equation by radius r, so we get s by r is equal to u by r into t plus half a by r into t square. This at we will treat as the acceleration along the arc of a circle, along the path of the particle, along a circular trajectory that it is taking. So s by r would become equal to theta. U by r would become omega naught. Now let me introduce that. Here it is, let's say velocity is u, and u is equal to r into omega naught. The starting point, initial angular velocity is omega naught, and u is the tangential velocity. U is the tangential velocity and angular velocity is omega naught. So therefore, this is omega naught into t plus half a by r. Now at by r would be equal to alpha into t square. Look at this equation. This looks just similar to this equation. Only thing is, this is about a linear translational motion, and this is about a circular motion. The circular motion can have acceleration, therefore velocity along the path, circular path, may change. If the velocity changes, there has to be a tangential acceleration, there has to be a related angular acceleration as well. Now we can get to this equation through one more way. Say for example, we have definition for an average angular velocity. Let's say average angular velocity. How shall we define that? Now let's say we are at angular velocity omega at some instant of time t later, and initial angular velocity is omega naught. Average value would be exactly this, omega plus omega naught by 2. Also, this is equal to the net displacement, angular displacement that it has taken, and the net amount of time that it takes for that particle. So the net angular displacement is theta in a net amount of time t. That can also define average angular velocity. Now, if we multiply or rationalize these things, we get omega plus omega naught is equal to 2 theta by t. Now replace this omega by your relation with the initial angular velocity through this relation. Let's say v. V is equal to u plus at. Here, if we divide by r, then u by r plus a by r into t. V by r would become omega. Angular velocity after time t. U by r will become omega naught. Angular velocity at the start of the motion. A by r will be at by r, and at by r is alpha. So that means omega is equal to omega naught plus alpha t. This is the second equation in circular motion, kinematical equation in circular path. So we replace this omega naught plus alpha t over here, and in that case we have plus omega naught as equal to 2 theta by t. Then twice of omega naught plus alpha t all divided by 2 and entirely multiplied by t would be theta. So this goes omega naught into t plus half remains this side, alpha into t square. So omega naught into t plus half alpha t square is equal to theta. Now see this. Now look at this. It's exactly the same, and this is what I was talking about, that you can obtain this in one more way. It's round and round, you can say. Just because there is a circular motion, just for the sake of fun, I'm saying this. Alright, now omega t plus half alpha t square is equal to theta. So we have how many equations? We have only two equations. Now let's say this equation we can rewrite in one more way as omega minus omega naught by t is equal to alpha. Let's say we take this equation and say for example we take this equation. So this is an equation of interest right now, and now let's say we multiply these two. So if we multiply these two, we have omega square minus omega naught square in the numerator product, 2t in the denominator product is equal to alpha theta by t. This is what we will have. Theta goes, and we have omega square minus omega naught square is equal to 2 alpha theta. T cancels both sides, and this is another equation which alternately says that omega square is equal to omega naught square plus 2 alpha theta, theta alpha. I hope you can easily guess that this can be otherwise obtained from, v square is equal to u square plus 2as. If we divide by r square, on both sides, then we have 2 a by r, s by r, and then v by r whole square. V is equal to r omega. So this is simply omega square. Okay, all right, I'll write this and finish off. And this is omega naught square plus 2 at by r. A is equal to at, as I stated, is equal to a. I'll write again. So a alpha and s by r is obviously theta. This equation is just the same as this. So what I mean to say is, you have still three kinematical equations here in the picture. This is, let's say, equation 1, let's say this is equation 2, and this is finally your equation number 3. These three kinematical equations can help us obtain the values of angular velocities or angular acceleration or the time taken for a certain motion or angular displacement along a circular path, when it is moving along a circular path under non-uniform pattern, or when the velocity of the particle is changing. Then we have angular acceleration existing, tangential acceleration existing, and like that. Now going ahead, we need to calculate the angular acceleration alpha, tangential acceleration a, and also some other acceleration if it exists in a circular motion. So let's go ahead on this. I'll just rub it off, and we move to the second idea, that if a particle takes a circular path, then how does its accelerations build up as it moves along its path. So here it goes. Let's say we take a particle on the circular path whose radius is 1 unit and centered at origin. For simplicity, we will take this, and let's say we have origin at the center of the path, and the radius is equal to 1 unit, and we will define the position of a point here. And in that case, let's say this is, say, let's say for example, this is the horizontal x axis direction, and let's take the position of the particle somewhere here, point P, and this angle is, let's say, theta. Then obviously this point P is at cos theta comma sin theta as coordinates. Then we can define a radial vector, r vector. The radius vector will define the position vector of the particle at point P, moving along a circular path centered at origin at a radial distance equal to 1 unit. So the magnitude of the radius is 1. Now the radius vector, however, changes. Let's say the particle is sometimes here, then the radius vector would be directed this way. This would be the radius vector. If the particle is here, then the radius vector would be directed this way. So that means we can have a general definition for the radius vector. Let's call it equal to r vector. Magnitude is equal to 1 unit, and components of I cap and j cap are cos theta and sin theta. So cos theta I cap plus sin theta j cap. This is your simple radius vector, or the radial vector you can say, and is directed away from the center. This is directed away from the center. This is how it is defined. Now, at any point, let's say there is a tangential vector. Now, look at this. This would be the tangential vector. Now, this tangent vector, how can we define this? So, what we do is, we take a sample evaluation. Let's say this is your x-axis, and this at an angle theta is your point P. This is the radius vector, and radius is equal to 1. And this would be your t vector. So how is this t vector? Making angles? Let's say with respect to horizontal, this radius vector itself, this extended line of the radius vector, can make an angle theta, just as this. And this radius is at a 90-degree angle to the tangent vector. So therefore, the net angle that the tangent vector makes with the horizontal is 90 plus theta. So therefore, the tangent vector, if it is having some magnitude, let's say 1 unit, has a certain angle of 90 degree plus theta. Like the radius vector is magnitude 1 unit and of angle theta. This is the equivalent polar definition for the radius vector. So that means the tangent vector can be defined as 1 as the magnitude into cos of pi by 2 plus theta I cap plus sin of pi by 2 plus theta into j cap. So therefore the tangent vector can be defined as cos of pi by 2 plus theta means minus sin theta. So minus sin theta I cap, and sin of pi by 2 plus theta means cos theta. So cos theta j cap. This is the definition of the tangent vector, whereas this is the definition of the radius vector. Now here we have two things: a radius vector defined radially outward and a tangent vector defined along the tangent. And the tangent is directed in the direction of the circular motion, tangentially in the direction of the circular motion. Let's say the particle is moving in this direction, so the tangent is directed along the tangent at the point where it is constructed and in the direction of the motion, directed along the particle's path. Now once we have this, the radius vector changes directions. So therefore, the particle experiences a change in position with respect to time. the rate of change, the rate of change of position of a particle with respect to time on a circular path. Look at this. There is a change in position. The particle is anyhow changing position, and that is happening with respect to time. So there is a rate of change with respect to time. So rate of change of position of a particle with respect to time on a circular path. How will you define this? The basic definition of this would be rate of change with respect to time of the position of the particle. As I told you, the radius vector can also be defined as the position vector. Can also be defined as the position vector of particle at a given instant of time. So if this is the position vector, that position vector is changing with respect to time. Now once we carry out this, how will we define dr by dt? I mean to say, what shall we call that? So dr by dt would be defined as the velocity of the particle, and that is tangential velocity, velocity of the particle along the arc of the circle. So this can be defined as the tangential velocity or velocity along the arc of circle. This is how we can define this. Now once we define the tangential velocity, we can also define the tangential acceleration. So therefore, let's first calculate this Vt as equal to d dt of r vector, that is cos theta into I cap plus sin theta into j cap, and that makes d dt of cos theta, that is minus sin theta into d theta by dt I cap, and d dt of sin theta means cos theta into d theta by dt into j cap. So simply velocity along the tangent or tangential velocity can be defined as d theta by dt, I hope you remember, is equal to omega. Here d theta by dt is the angular velocity. So therefore I have that common, and omega comes out, and omega comes out, and then this comes out with vectorial dimension as minus sine theta I cap plus cos theta j cap. Now you just make a matching. This is the tangential vector, tangent vector, and this is the tangent vector. That means this velocity with this magnitude will be directed along the tangent of the circle. Now time for the generalization. Let us say I will make changes right from the beginning. I have always considered a unit circle so far. Now I am making changes. I hope you will be able to relate. When we started with these position vector definitions, then I said that this is a unit circle. That was for simplicity. I had stated at that moment. Now I will say that no more it's a unit vector. It can be a circle with any radius. Let's call it r. Let the radius of the circle be r. And if we go that way, then the position vector of the particle shall be defined for a magnitude of r. And then the radius vector will have a magnitude of r. And like this. The idea goes forward, and we keep this radius as an r. We keep this radius as an r. And the tangential velocity therefore shall be defined with this as a unit vector, with this as a unit vector. Let it remain like that. No change in the tangential velocity. This is just for the direction, a unit vector. Now rate of change of position of the particle will go for the derivative of r vector. So the derivative of the r vector will contain, just like here, a product factor of r. Let's say like this. Then what? This r being a constant can come out of the calculation, and therefore this will have an r as a multiplier, and then therefore this particular r will stay outside. And now you observe the magnitude of this is equal to r omega. We had seen that s is equal to r theta. We had seen that s is equal to r theta. We also saw that ds by dt, that is rate of change of the position of the particle with respect to time along the arc of a circle, is ds by dt. That should be tangential velocity, and that should be r into d theta by dt, and therefore vt should be equal to r into omega. This was the magnitude. It was a scalar calculation. This is a vector calculation, and we are there at this vector calculation confirming the magnitude vt equal to r omega, and also you can say the direction of this tangential velocity, which is along the arc in a tangential direction along the path of motion of the particle. So now we have the particle moving. It has gained velocity. Now maybe this velocity can change. And if the velocity changes, then it will be an accelerating particle, as can happen in any circular motion. This is quite possible. So then let us define something which is rate of change of velocity, tangential velocity, along the arc of a circle. So then the rate of change of Vt with respect to time, this should be equal to acceleration. And what type of an acceleration? This should be a tangential acceleration. Do you think this should be alone and alone tangential acceleration? No, I will not define it like that. I will just say that the particle is having rate of change of speed along the arc, and as a result its direction is also changing. The direction of the particle, the tangential velocity here will be defined this way. This is tangential velocity. The tangential velocity here will be, defined tangentially like this, and the velocity can be directed this way. So the direction of the Vt is changing at every position on the arc of the circle. It's a vector. So when you're changing position, your velocity has two attributes. One is its magnitude, which may or may not change. Another is its direction, and due to the change in direction, something might happen. And let's see what can happen. Rate of change of Vt with respect to time, therefore, I will define simply as the net acceleration on the particle. Let's define it like this. So therefore, the acceleration I will define as equal to a vector, and it will be d dt of Vt, and then we will get the derivative of this. We will calculate the derivative of this. Now here is a mathematical challenge. You have to differentiate r omega into minus of sine theta I cap plus cos theta j cap. That's all. Now here this omega, if it is a constant, then your Vt would be a constant. And if Vt is a constant, then are we calculating this as a zero? So let's consider omega as a variable, so that Vt changes as omega changes. As angular velocity increases or decreases, Vt can increase or decrease, and that means we are having two elements in this product which we need to differentiate. So we apply product rule, and we get the A vector as equal to R outside and inside omega into d dt of minus sine theta I cap plus cos theta j cap, and plus this minus sine theta I cap plus cos theta j cap into d omega by dt, into d omega by dt. Let's finish off this. This is how it goes. means first factor into derivative of the second plus second factor into derivative of the first. What exactly is d omega by dt? So we define d omega by dt as equal to alpha. I hope you remember angular acceleration. Now when we differentiate, what exactly we have is like this. Omega into ddt of minus sine theta would be equal to minus cos theta I cap into d theta by dt plus ddt of cos theta would be minus sine theta into j cap into d theta by dt, and I realize that I am going to have less space than needed, plus minus sine theta I cap plus cos theta j cap into alpha as defined here, alpha. So when we let's say apply this over here, we are having some surprising result. I hope you'll appreciate this. D theta by dt is omega, comes out. So we have omega square, and what remains inside is minus cos theta I cap minus sine theta j cap, and thanks for your patience. Minus cos theta I cap minus sine theta j cap plus minus sine theta I cap plus cos theta j cap into alpha. Now, here is a secret of circular motion. We have two different types of calculations. If you observe, minus taken out will build cos theta I cap plus sine theta j cap, which we know what exactly is that. And I also know what exactly is this. So, time for making some space. I'll just rub this small things off, and we can write the resultants very easy. And here you go. Here you have ample space. Now you see, that means acceleration here, the acceleration here is equal to omega square r into, what would you call this? I take the minus out. I take the minus out. Cos theta I cap plus sine theta j cap, and plus I will write it just below, plus minus sine theta I cap plus cos theta j cap into alpha. Now we are done. We are done. We are done. We are not done. We are not done. Just a moment. R into alpha. So this side I would like to multiply R into omega square with a minus has been taken here, and I think we should have R into alpha here. So R into omega square with a minus coming out and the remaining things plus R into alpha and minus sine theta I cap plus cos theta j cap. This is how it goes. So R goes with both the factors, R omega square and then R alpha here. Time for finalization. Minus omega square R is a component that works entirely along the radius vector. So I will attribute this minus sign with the radius vector, and then what we have is something like this, minus of the radius vector, and plus let's say plus r alpha into what? R alpha into what? What exactly is this? This is the t vector. Now you see, t vector. So yes, I remember we had changed this to magnitude of r, and I should consume this r with this to write the minus of r vector. So I will alter this as well. So that means we can write in short that minus omega square r into minus of r cap. How about that? Where r cap is the unit vector. R cap you can define as r cap is equal to cos theta I cap plus sine theta j cap. This is how you can define the unit vector along a radius outward away from the center, and this is towards the center, negative of r cap, and plus r alpha into t cap. This is in fact a unit vector, and this is the net acceleration. This is all that you got. This is the acceleration. Now, how do you read this? The reading of this calculation is simply going to be bidirectional. You can say mutually perpendicular in direction, and has two significant components. We will define, let's say, we will define minus omega square r into r cap. This part, omega square r into minus r cap, is actually the radial acceleration and is directed towards the center. Now, surprisingly, why towards the center? Now, say this. Alone r cap, only r cap was directed outwards, was directed away from the center. So, obviously, minus r cap would be directed towards the center. So, therefore, we say that minus r cap would be directed towards the center. Minus r cap would be directed towards the center. So, this is guided towards the center. This acceleration is directed towards the center. This is what we call as the centripetal acceleration. And what exactly is this? R alpha, and we can call this AR, the radial acceleration, AR. And what about this? This is the tangential, the other part, R alpha. R alpha into T cap. R alpha into T cap would be the tangential component, the tangential acceleration guided along the tangent, as you can see, with a magnitude r alpha. I hope you remember here omega any velocity, tangential velocity was equal to r omega, and tangential acceleration was equal to r alpha. We had calculated this earlier, and this came up with the same magnitude, and the direction is also now determinable, and therefore the tangential acceleration is also guided in the same direction. AT vector and the VT vector are directed in the same direction, and this is about the net acceleration. So this defines the net acceleration of a particle along a circular path. Net acceleration of a particle along a circular path is given by this centripetal acceleration as one part of it, and the tangential acceleration as the other part of it. Thanks for your patience. It was quite a long discussion. See you in the next part. Stay subscribed. Thank you.